Thank you for being with us today. I'm happy to see all of you here for this talk, which is part of this year's Get to Know Your Neighbor Seminar Series. With the seminars, we provide a platform of cross-school exchange for our EPFL community. Last month, we had the pleasure of hosting Professor Bruno Correa from the Laboratory of Protein Design and Immune Engineering. Today, we're delighted to have Professor Nicolas Boumal with us, who's going to give a presentation on geometry and symmetry in non-convex optimization. To give you an idea of what to expect, the seminar will last for approximately 1 hour, with Nicolas presenting for roughly 40 minutes. This will then be followed by a Q&A. So please, if you have any questions for Nicolas, feel free to submit them already in the chat. We will collect and discuss them during the Q&A session. You'll also have the opportunity to unmute and ask your questions directly, which worked best in the past for us. Before diving into the presentation, I would like to thank Nicolas and the team for organizing this event, and I'm happy to pass the screen to Nicolas now.
All right, thank you, Jan. Can you hear me fine, and can you see my screen?
All good.
Okay, great. Okay, fantastic. Well, first of all, thank you for the opportunity to introduce myself to the CIS community. I joined the EPFL in July. I haven't met very many people yet, but I'm sure this will change soon enough. So with this talk, what I'd like to do is to present some of the ideas that we are thinking about in my group about geometry and symmetry, and more generally about optimization. And I'll try to keep this at the high level, sort of give you a taste for the flavor of the results that we're looking at, the algorithms we're studying, the applications we are thinking about. All right, so picture yourself back in Göttingen in Germany in 1854, and here we are standing in front of the university library over there, and a young Bernard Riemann is walking around the streets of this university campus, and as he usually does, he is thinking about some problems. He's always thinking about the next thing he wants to solve, and specifically these days, what he would really like to do is to find a way to recommend movies on Netflix to his friends based on the movies that they've seen. And the other thing that he would really like to do is, based on very many pictures of a 3D object, he would like to automatically compute a 3D computer model for that object. And he's thinking about these problems, and then he does what any reasonable person in that situation would do. He invents Riemannian geometry because it seems to be the right thing to do for that task. Well, okay, it's not really why he did it. And at the very end of the talk, I'll say a little bit of something about why he invented the geometry that later became known as Riemannian geometry. But in between now and the end of the talk, I hope to convince you that indeed this kind of mathematics actually plays an important role in those applications, and for good reasons. So we'll get to that. And so on our way to this resolution, I'll talk about optimization, which is what we do in the group, and specifically about continuous optimization. So I imagine everyone in the audience, although we have a rather diverse audience, but certainly everyone has encountered optimization, is familiar with it to various extents. It comes up in inverse problems when you're doing imaging, in statistical estimation when you're doing maximum likelihood estimation, in machine learning when you're training a neural network. One way or another, you take this application and you formulate it, you model it as, I want to minimize some function f over some sets. And the function and the sets are defined by the model you take and the data you have for your application. And depending on the structure of that function and the structure of that set, you may have various algorithms that you may choose from to try, to solve it and run them. And the performance that you get, the guarantees that you may get, can vary widely. And at a very general level, the kinds of questions that we like to ponder in optimization would be, which structures are tractable? What kinds of properties could the function have? Could the set have that would make my life as an optimizer comfortable? All right. And the traditional view of that, tractability frontier, as it stood certainly in the 90s and throughout the 90s, and is only gradually changing, is that you had all the problems that are convex, which I imagine many of you have heard of. So in blue here on the screen, you have all the optimization problems that have this nice mathematical feature of being convex. And you have all of the non-convex problems, on the orange side of the screen. And back in the 90s, the idea was that the frontier of tractability, the black line here in my cartoon, stood somewhere like this. That if you're on the left side of the black line, so most convex problems, we can solve. And things on the other side of the black line, essentially, anything non-convex, we don't really have strong ideas about how to solve it. Okay, but this picture, this perspective is changing rapidly. And this is the essential, area where my group works, where I work. Okay, so what's the big deal about convexity and non-convexity? Well, at a very cartoonish level, the thing we like about convexity, which I'm not defining, I'm just illustrating, is that local information can give you global information. Okay, what I mean by that is when you have an optimization algorithm, when you implement an optimization algorithm, the rules of the game usually are that you get to evaluate the cost function or its derivatives, and I'm just not talking about the set right now, at particular points. But when you do that, you only get local information about the behavior of the function around that point. On the other hand, what we're trying to do is we're trying to find a point that would be, let's say, a global minimizer for the function. So a point where the value of f is smaller than anywhere else, which is a global kind of characterization. So there's a mismatch between the information we get access to and the target that we have in mind. And convexity is this feature that an optimization problem may or may not have that connects the two. And for example, for the case of a differentiable problem, you'd have this property that if the gradient at a point is 0, which is local information, then you can be certain that the point is actually a global minimizer, okay, which is a very powerful tool to have. And when your problem is not convex, it might look, anything like this. And now we have this very unfortunate situation where many points could have this property that the gradient is 0, but only one of them is a global minimizer. And then you can look at further finer characterizations, local characterizations, such as saying, well, I don't just want the gradient to be 0, I also want the second derivative, the Hessian, to be positive semi-definite. And those are known as the second order necessary optimality conditions. And I'll come back to this a lot during the talk. The second order necessary optimality conditions, in this case, are still not enough to uniquely characterize the global minimizer. So non-convexity can be bad. But the semantic point, and it's kind of an obvious point, but it's important to keep in mind, is that non-convex just means not convex. It just means that the nice guarantees of convexity do not apply. It does not mean that the problem is necessarily hard. And in this cartoon, we see an example where second order necessary optimality conditions are actually sufficient to characterize the global minimizer. And so if you can find that point, you can solve the problem. And many of the examples I'll discuss going forward will be exactly of that form. All right. Okay, so what do I mean then when I say that a non-convex problem is not so bad? What do I mean when I say that a non-convex problem is benign? Well, it can mean a number of different things that are sort of on a spectrum. And through this slide, I'd like to give you a taste for the kind of theorems that we try to prove in this field, the kinds of results that we're trying to establish. And there might be some very strong results, such as the first line, which would say, under some conditions, and the conditions could be, conditions on your data. It could be very generous, like saying for all data or for almost all data. Or it could be something a bit more restrictive, like if your data follows some probability distribution that is not, playing against you, it's not adversarial, then maybe something happens with high probability. So under some conditions, you'll get something, and the something you get, something very strong to get, would be that necessary optimality conditions, for example, at first and second order, would somehow turn out to be sufficient for global optimality. Okay, this is called landscape analysis. It's a very strong result because it's not tied to any particular method. It's just telling you, look, this is a feature of that cost function you're trying to minimize. And if you have any reasonable algorithm that can find points that satisfy those local conditions, then you're actually solving the global problem. Okay, so this is a very nice result to have. And on a somewhat, other side of the spectrum, still satisfying, but not as satisfying, there you would find results of the form, and there's some conditions on your data. There's a particular algorithm, maybe gradient descent, for example, and we know how to initialize it sufficiently well, not too expensively, such that if you run gradient descent starting from that point under some conditions on your data, the sequence generated by the algorithm will lead you to an interesting place. It's not as satisfying because if you want to use a different algorithm, the theorem doesn't really allow you to do that. But sometimes it's the only thing we can prove. And sometimes it's the only thing that can be proved because the landscape actually does have bad points, but somehow we can work around them. All right. So back to this picture, and with this notion of benign non-convexity in mind, something that has been happening over the last number of years, I don't know if it's 10, 15 years, depends how you count, is that bit by bit, we have identified, the community at large has identified what I would call pockets of benign non-convexity. So examples of non-convex optimization problems for which it turns out that we have really good theory. We understand that they can be solved, we know how to solve them. So this is, strongly suggesting this frontier of tractability, should be shifted, at least somewhat. And the big question, which, if you ask me, is a very long-term question. I don't think we're anywhere near, resolving that one, but it's a good one to think about. Is, what characterizes this frontier? If it's not convexity, and I'm sort of, not acknowledging what's going on over here, which is, a separate story. But if it's not convexity, then what structure do these good non-convex problems have that can sort of explain why they're so nice? And to try to go in that direction and to try to address this question. There's something that is very useful that Ju Soon, he's an assistant professor at the University of Minnesota. He's been working on this for a number of years. He himself does a lot of research in non-convex optimization. And some time ago, he decided to build a list of research papers that talk about examples of benign non-convexity. And when I was checking and preparing for this talk just last weekend, he had roughly 900 papers on that list. It's not an exhaustive list, but it's a curated one. And he organized those 900 papers in a number of categories that you can see here. And something that's very interesting to do is to just look at all of these examples and wonder what do they have in common? Maybe not what do they all have in common. That's kind of a difficult thing to do. Haven't identified something like that, but what is something that many of them have in common? All right, and this is now connecting to the title of this talk, which was about geometry and symmetry in non-convex optimization. Something that you see a lot in those examples is geometry and symmetry. And I'll talk about them separately, but they're always sort of interconnected. Right, so for the first point, first common thread that we can recognize is geometry, by which I mean a lot of those problems that we happen to be able to solve, the search space, the set over which the cost function is defined, the search space is a smooth manifold. So it's a nonlinear set. I mean, it's allowed to be a nonlinear set. In those examples, they will be. They won't be linear. But you can linearize them around every point, which is what qualifies them as smooth. So think as a sphere, for example. And these sets, they are not convex. So the sphere, not the ball, right? The sphere is not convex. The ball is convex. The sphere is not. So if you're optimizing over a non-convex set, then right off the bat, the optimization problem cannot be convex. But it's not necessarily the case that anything that's happening on such a space is necessarily hard to solve. So this is the first way where somehow this geometric structure makes it impossible for the problem to fall under the umbrella of convexity theory. Yet there's no immediate reason why it should be hard to solve. So back to this list. some examples that I'm going to look at. There's going to be 4 for this first one. Will be the ones highlighted here. And let me just go over them bit by bit, and at a very high level, explain why, where exactly does the manifold come up in those applications. And I'll make a statement about how benign their non-convexity is. All right. Okay. So let's go for the first one, which I'm sure everyone has heard of. It's sort of, I guess, principal component analysis has maybe a different name in every scientific field because everybody came up with it because it's so important. It's this task where you have a data set. It's a cloud of points in a high dimensional space. And we are looking for a lower dimensional subspace that fits the data as well as possible. Okay, that's one take on principal component analysis. You might call it principal subspace analysis. And if you write this down from an optimization perspective, then what you would say is, I'm trying to find among all possible subspaces of a certain dimension, among all possible planes in R3, I'm trying to find the best one. And what it means to be the best one is that when I calculate a certain cost function, that would be a least squares loss of fitting the data points to the plane, that this thing should be minimized. And so PCA is an optimization problem. And the search space, the set over which I'm optimizing, is the set of all possible subspaces of dimension D in this bigger space. And that set is a little bit abstract, but it's something you can work with. It's called the Grassmann manifold. Right, so PCA, one way to see it is it's optimization on something called the Grassmann manifold, the set of all subspaces. Another perspective on the same problem, which is one you might see in a matrix analysis course, is that when you have this data set, you can arrange your data points as columns in a matrix. Now you have a big matrix X, and PCA is actually equivalent to finding the matrix of rank D that is as close as possible to your data matrix. You're trying to approximate the data matrix with a rank D matrix. And again, the set of matrices of rank D, so fixed rank, fixed size, that set, which is a subset of all matrices, happens to be a smooth set. It happens to be a smooth manifold. So from this different perspective, PCA is again an optimization on some manifold. They're non-convex manifolds. The problem is non-convex, yet the non-convexity of this problem is entirely benign. And to be more specific, the second order critical points, so points which satisfy second order necessary optimality conditions, all of them, always, they are global optimizers, no conditions on the data. Okay, it's the nicest non-convex problem ever. And sort of intuitively know that it has to be so nice because we all know that we can compute PCA, and usually we do that using SVD. All right. So this is one example where things are very, very nice. A related example, which I imagine many of you have heard of too, it was very much in fashion 10 years ago, is the low rank matrix completion problem, connecting back to this idea of Netflix that I mentioned earlier, where there's a big matrix that we're interested in figuring out. And each row in that matrix corresponds to a person, a customer of Netflix. And each column corresponds to a TV show or a movie on Netflix. And so each entry in the matrix corresponds to a person and a movie. And the value you'll put in that entry will be the rating that that person gave to that movie. Okay, and most of the entries in the matrix are unknown, simply because most people didn't watch, most movies. But there's an interest that you can easily imagine in trying to figure out those entries, which I don't know. What is the value in those entries? What can I estimate that? Because if I can do that, then I can start doing recommendations. All right. Now there's a good backstory that I'm not getting into for why this complete matrix that we're trying to figure out might actually have low rank. Let's say rank D, where D would be a parameter that you'd have to fix somehow. And so from that point of view, you can write down this problem again as optimization. Your search space again would be the smooth manifold of rank D matrices. And your cost function would measure how a least squares fit not to the whole target matrix, because we don't know it, but to the entries of the target matrix that we happen to know. So it's exactly like PCA, except there's missing data. And in fact, most of the data is missing. We knew PCA was easy from a non-convexity point of view. It turns out, but it's a lot harder to show, that low rank matrix completion, this missing data PCA, is also easy, but you have to be a bit more subtle about what the statement is. And there's some conditions on the target matrix. It has to be incoherent, which means something. And the samples, the entries that you get to see, you should have sufficiently many of them, and they should be sampled in a certain way, blah blah blah. And then with a high probability under those conditions, second order critical points are optimal. So again, the non-convexity is benign with some caveats. All right. Now, a third application, still talking about geometry and benign non-convexity, a third application, this one's a bit maybe more surprising, is community detection in networks, in graphs. So in this one, imagine there's a large collection of people that we're going to abstract into nodes of a graph, of a network, and they are partitioned in two communities, but we don't know who belongs to what community. Okay, there's the reds and the blues. We don't know who's what. But what we do get to see is the edges in the graph. We get to see which pairs of nodes are connected. And we are told that if two nodes are connected, it is more likely that they have the same color than not. All right, we're saying nodes in the same community have a higher probability of being connected than nodes that are in distinct communities, right? And so given the edges of the graph, but not the colors, the task is, can you figure out what the two communities are? Can you separate them? This is not an optimization problem on a manifold, right? It's a combinatorial problem. For each node, you need to decide if it's red or blue, if it's +1 or -1, okay? And in fact, this is a hard problem when you state it this way. Well, unless you add some conditions, which I'm going to do in a second. All right. Now, the way you can map this and with good results into an optimization problem on a manifold is to relax. And what it means to relax in optimization means to make your search space bigger in the hope that it's going to make it easier to optimize. And the perspective here is to say, well, +1 and -1 are 2 points on the real line, okay, -1 and +1, and this is the real line. Now I can look at this, in a plane, and instead of thinking of +1 and -1s as points on the real line, I can think of them as points on a unit circle in the plane, right? Why not? You can do that. The circle is a manifold, okay, it's a smooth set. And now instead of trying to assign a +1 or a -1 to each node, I'll try to assign a point on the circle to each node. Okay, which is not quite the original task. But if you do that, now you have an optimization problem over a Cartesian product of many circles, a kind of high-dimensional torus, if you will. And it turns out that in statistical regimes of interest, okay, there's a random model lurking in the back of the vague language that I have on the slides. You can argue that in some regimes, with a high probability, the solution, all the second order critical points for that non-convex problem with a high probability, if you get one of those points, you can round it, you can transform easily that solution, which gave a point on the circle to each node, into a +1, -1 label. And those labels will form a good estimator, which is defined in some precise sense. So you see how gradually the strength of the benign statement is sort of becoming weaker. Okay, we had to relax the problem. I'm not saying we get a global optimizer. I'm saying after rounding with high probability, you get a good estimator. Okay, so that's a third application, a third example where these things come up. And then a fourth example, and I won't get into any of the details here because it would take quite a while, but it's an interesting application, I believe, is something that comes up in robotics with something, it's called simultaneous localization and mapping. And here, the situation is that you have, let's say, a Roomba. Okay, so these autonomous vacuum cleaners that you can have in your apartment, and imagine that it's moving around your apartment, and it has to continuously figure out where it is in the apartment, and also to figure out what its orientation is. Okay, it's rotating around some axis. So when you model this, when you write this down, I mean, there's a long pipeline, SLAM, simultaneous localization and mapping. It is a rather sophisticated application. But when you write it all out, one of the parts in the computational pipeline of this problem is to estimate these orientations and these positions of the robot at different times. And this naturally becomes an optimization problem over a manifold. Why? Because the set of orientations is a manifold. It's certainly true in the plane, right? So the orientation is really just a circle. It's the set of all angles. That's what we had on the previous slide. But it's also true in 3 dimensions, and it connects with other applications as well in computer vision. It turns out with basically the same kind of math as we had for the network community detection problem. Again, you can relax this kind of problems and show that there is a very strong form of benign non-convexity that is sort of hidden in these formulations. And you can solve many of those problems quite efficiently and with good guarantees using optimization on manifolds and on rotation groups and on some relaxations with the Stiefel manifold. All right, so I won't say much more about this. And hopefully this gives you a sense of examples of smooth manifolds, low rank matrices, the Grassmann manifold rotation groups, the Stiefel manifold circles that come up in applications fairly naturally so, and for which we have examples of benign non-convexity. That was the common thread number 1. The common thread number 2, which I'll illustrate with just 2 examples, is symmetry. And here the story is that if there is symmetry, if there is redundancy, if there is a non-identifiability, if there is in your problem, then this can structurally make it impossible for the problem to have convexity. Yet there's no particular reason a priori why symmetry should necessarily make all optimization problems hard. Okay, it's certainly not the case. And we can see this, visualize this at a cartoon level. So let's focus on this one first. So this is an example. What we're seeing here is a function f of xy, right? The surface represents a real function of 2 variables, x and y. And I built this function in such a way that it has a permutation symmetry, a discrete symmetry. So f of xy is equal to f of yx. If you permute x and y, it doesn't change anything. Now, because of that, if there's a global optimizer over here and it's isolated, then when I permute x and y, there's got to be another global optimizer over here, also isolated. And because they're isolated, when I try to travel from one to the other, I necessarily have to go through a valley, through a saddle point, through a point where the gradient here is going to be 0, but it's not a local minimizer. So this kind of structure immediately makes it impossible for the cost function to be convex. Yet when you look at this function, it's completely obvious that if you try to optimize it, things will be fine. Right? If you run gradient descent on this, it's just going to go to one of the minimizers and things will be okay. Similarly, if you have continuous symmetries in your problem, so here, this is an example of a function in R2 that has a property that if you rotate the point, so if you rotate the plane, the cost function does not change. Okay, and so if there's a global optimizer here, then there's got to be a global optimizer along this whole circle. And because of that, you can easily convince yourself that there has to be, is not a saddle point, but a local maximizer here in the middle, a point where the gradient again will be 0, but it's not an optimizer. And so again, the symmetry, continuous symmetry here, makes it structurally impossible for the problem to be convex. And yet, it's a trivial one to solve, right? That's kind of the point. So what I'll do now, looking at 2 examples, is, back to this list of Jusun, is sort of look at 2 examples of non-convex problems for which we have good benign, good results regarding how they are benign, their non-convexity is benign, and where symmetry is actually a big part of the benign aspect. Okay, so one of the examples will be very vaguely related to deep learning, but don't get too excited. I'm not going to talk about anything that's actually relevant to deep learners. It will be something about linear neural networks, because it will be easier to make my point. Okay, but I'll get to that in a second. Okay, so two examples. And the first one is orthogonal dictionary learning. So in this one, I'll have discrete symmetry. Okay, so this was this cartoon. So what is this problem? Probably many of you are familiar with dictionary learning. It is the following task. I have a data set. Okay, so the matrix X, the columns of X are the elements of my data set. What I would like to do is to find a basis. So a set of vectors Q1 to Qn, and I collect them in a matrix Q. And in fact, in this particular version, we're going to ask that Q be an orthogonal matrix. So the basis should be orthonormal, okay? Hence the name orthogonal dictionary learning. I would like to find a basis, Q1 to Qn, such that every element in my data set has a sparse representation in that basis. So I can write each column of X as a sparse linear combination of the basis vectors. And one way that you can write this as an optimization problem is as follows, where A will be the matrix that contains the coefficients of the linear combination. So when I multiply Q with A, this will contain all the linear combinations that I'm crafting of the basis vectors Q, and I would like them to match the data set, right? I want the data sets to be expressed roughly as Q times A, and I want A to be sparse. And so to enforce this, to favor this, we can add this term in the cost function. Okay, this is work by John Wright's group. And we're asking that Q is orthogonal because it's orthogonal dictionary learning. And when you look at this cost function, it has a lot of discrete symmetry. Specifically, I mean, intuitively, it's clear that if you change the order of the basis vectors, it shouldn't change anything, right? And indeed, it does not change anything. If you permute the elements of Q, this is going to, permute Q, you'll permute A accordingly, but that's not going to change the sum of absolute values of the entries of A, okay, the magnitude of the coefficients. Likewise, if you change the signs of the basis elements, it's also not going to change anything to the actual problem. So the cost function is symmetric under those discrete symmetries, is invariant under those symmetries, but there's an exponential number of equivalent points. And so it's creating this exponential number of valleys and spurious points and saddle points and all of that. But somehow it's not making the problem harder. And in fact, this is something that they were able to make very precise. Okay, somehow the symmetry does not actually break anything fundamental. So that's one example. And the second example is looking at linear neural networks. So not something that you would actually use in the practice of neural networks. So in this one, but a lot of people have been interested in this, and I'm sort of working off of these publications here. In this one, the activation function is just the identity. So when you have your data set X and you push it through the first layer of the neural network, it's going to get multiplied by a first matrix of weights W1, and then you'll get to to this point, and then you push it to the next layer, which multiplies with W2, etc., until you get to the end, and you multiply it with WL. And now you look at what you get on the output, and you would like for that to match the labels Y. And so your cost function, your empirical risk, your loss is this function F. It's a function of the weights in all of the layers, and you're trying to minimize, this very nice least squares loss. This thing is non-convex because you have a product of matrices, but in a way, it's the non-convexity is there by accident, if you will, because you can see that this function F is really a composition of this very simple function, which is convex, G, a function of a single matrix W. It's a composition of this function with this map here, which, given all the individual weight matrices, takes their product to represent what the whole neural network is actually doing. Okay, so if you compose this with this, you will get that. This function is convex. This one is not. But the reason is just that this mapping here has a lot of symmetries. There are many, many different ways of choosing the matrices W1 to WL that will give you the same product. So there's redundance in the parametrization. And this is actually the only reason why this problem eventually, might have been complicated, but it is actually not. Okay, there's another, there's a few other technicalities to this, but are not too important to the point, and they're not negating the point that I'm making. All right, so again, this is an example where there's a continuous symmetry. So what we saw here in the examples, there were a number of them, is situations where we have an optimization problem. It's not convex, and we somehow have results that are telling us that if you can find a point which satisfies first and second order necessary optimality conditions, then under some conditions, these points are actually useful for the downstream application you're trying to solve. They're global optimizers, they're good estimators, they're good networks, whatever that may mean. Okay. So naturally then the follow-up question is algorithmic, and it is, okay, a lot of those functions were defined on smooth manifolds. How do I find second order stationary points on a manifold? And this is where Riemann comes in, okay, kind of late in the story. What Riemann did, not for this purpose, but it's useful for our purpose, is to say when you have a smooth manifold, what does that mean? Well, it means that at each point of your set, there is a good notion of linearization. You can linearize the set around any point. Right? So certainly it's true on the sphere. I'm sure you can all imagine it right now that you can linearize the sphere at any given point. What Riemann said is, well, on each one of these linearized spaces, of these linearizations, I could define an inner product, make it a Euclidean space. If you do this in a principled way, you get what is now called the Riemannian structure. So all the tangent spaces are equipped with an inner product. And the great thing about that for optimizers is that Riemannian structures, they give you, a very well-defined notion of gradient and Hessian, which is essentially, exactly what we need as optimizers. If you think about gradient descent, if you think about Newton's method, if you think about trust region methods and all sorts of variations of those algorithms, and SGD and whatever you want, you need notions of gradients and Hessians. And Riemannian structures are, in a way, the broadest mathematical framework that will afford you these notions. This leads to the idea that on Riemannian manifolds, on manifolds equipped with a Riemannian structure, we can optimize. And this has led to a rather far-reaching extension of the general concepts of unconstrained optimization. These ideas started to appear in the 70s, and it was kind of a theoretical topic at the time. But then the numerical analysis and numerical linear algebra communities got involved in the 90s. And since then, it's been if you ask me, for my very biased opinion, a very practical way of solving optimization problems. All right, so at a high level, how do these methods work? I'm just going to sketch it with some cartoons again, but it's probably exactly what you're imagining. Remember how gradient descent works in a plane. Just for a flat space, you have your cost function defined, we see here the level sets. You start somewhere, you compute the negative gradient, and then you move away from your current point along that direction for some distance, you get to a new place, and then you repeat. Okay, negative gradient, direction, you move away for some time, and you get to a new point, etc. If you do this well enough, we know that this will bring you to a good place. If you're in a manifold, you do sort of the same thing. You start somewhere. Okay, we have a point here. At that point, you linearize, you have a tangent space. Riemann tells you, what is the negative gradient. So you compute that, gives you a tangent vector, a direction. And now you move away from your current point along the chosen direction for some distance, and you stay on the manifold. That's important. And you get to a new point and you repeat. And again, if you do this, well enough, this will bring you to a good place. And I'm not getting into any of the details here, but a lot of the things that I've been interested in and that we're interested in the group is, analyzing various types of algorithms that work on Riemannian manifolds in general and proving, whether or not they will converge to first order critical points, second order critical points, how fast they will do so, etc., etc. Okay, and so all of these things you can do. You can find second order points in manifolds, and there's a number of people interested in this. All right. So sort of as an unsubstantiated claim here, just with a blank slide, I'm just going to claim that these tools are actually quite efficient numerically, and there's a lot of literature to that effect that I'm not getting into here. And if you have a sense, in the spirit of the get to know your neighbors talk, if you have a sense that maybe some of these tools might be relevant or useful in applications that you're working on, I would be absolutely delighted to have a conversation about this. So feel free to reach out to me, and I'd be happy to have a chat about this. All right. So back in Göttingen, if Riemann did not invent his geometry to pick Netflix movies, then why did he invent it? Which is sort of a natural question, I suppose. And well, he probably had two reasons. One of them is that his advisor asked him to write a Habilitationsscript, and so he had to do something. And his advisor was Gauss. And Gauss, at the time, somewhat earlier, had figured out a way of understanding curvature of spaces in 2 dimensions and spaces in 3 dimensions. And that led to the Theorema Egregium and some very famous results there. And what Riemann, Riemann had this idea for how we could understand curvature for spaces in arbitrary dimensions. And this is what Riemannian geometry is all about. It's a mathematical device to describe and understand and study curvature of spaces in arbitrary dimensions. Yet nothing I've said in this talk had much to do with curvature. It didn't really come up. So it's kind of an interesting question in my view, that at this point, even though there's more and more papers that address parts of this, we don't really understand the effect that curvature may or may not have in optimization. I cannot really give you a straight answer for, is curvature a good thing or a bad thing for optimization? Like, it's at that point, right? But there's more and more literature and so this is an interesting, there are some interesting questions there. It's a story for another time. All right. So to conclude, let me advertise some resources that you may find useful if you get interested in these topics of optimization on smooth geometric sets. There's a book from 2008, which is the de facto reference book in the field, Optimization Algorithms on Matrix Manifolds. More recently, I wrote what is for now still a draft of a book, but you can get it on my webpage. It's fairly complete. An introductory textbook to this field, and I'm using this to teach here this semester at EPFL. And if you're interested in trying these things in practice and you need some software to get started, then there's a toolbox I've been working on for quite a while. It's called Manopt. You can get it here. There is a tutorial. There's a forum where you can ask questions and a human will answer. There's a MATLAB version, and 2 great teams have started working on a Python and a Julia version. And I encourage you to have a try. And with this, I thank you.
Okay, then maybe allow me to close the seminar. Thank you, Nicolas, for the presentation today. I would like to thank all of you, of course, in the audience for attending the event. The next events we have lined up for CS. So on April 19th, we'll host Sahand Hamal Rahi for the next monthly Get to Know Your Neighbor seminar. The week later, the 26th of April, we are delighted to host Professor Daniela Roos. She's the director of the MIT Computer Science and Artificial Intelligence Laboratory in Boston. She's going to speak at the CS colloquium. And with this, I wish you all a great day. Thank you, and we hope to all see you soon again at one of our next CIS events. Stay safe.